The purpose of today's lab, always phrased in the form of a question, of course, is what is the coefficient of friction between two dry wooden surfaces? So effectively, you're going to take a wooden block, and that wooden block has some masses in it. You're going to put that wooden block on a wooden track, and you're going to find the coefficient of static friction between those two pieces of wood, between those two dry wooden surfaces. Now, how are we going to do that? Well, as we go through that procedure describing how we're going to do it, I want you to keep in mind variables. You have to list, that's the first thing that you got to list on this lab is your variables, or at least the first thing you got to do yourself, because I've already given you the problem. List the variables. There's going to be one manipulated variable, and you'll see in a few moments as we go through the procedure, I think, what the manipulated variable is. One responding variable, you should see what that is as we go through the procedure. And then control variables, you know that I want you to list the important control variables. There might be 1,000 control variables. You need to list the one or ones that are particularly important, critical to not messing up the results for this lab. Now, the materials, I haven't listed them here, but I've taken a picture of it here. You're going to use a protractor. I've got protractors, don't worry. If I could spell it. You're also going to use a wooden track. You're going to use a wooden block. And you're going to use masses that go inside that wooden block in order to change the mass here. Now, there's one more thing that's not on there that you're going to need. If you've got a wooden block and you've got masses in that wooden block, then odds are you need the mass. You need how heavy it is. So we're going to use a triple beam balance scale to find the mass of this block and the masses inside the block. Now, for logistics' sake, since we only have 3 triple beam balance scales and we're going to have to share, what I would suggest you do is find the mass of the wooden block using the triple beam balance scale. And as far as the rest of the masses, as you change the mass from trial to trial, you can just add these masses to it, right? The mass is printed on this. So if this is 50 grams and this was 200 grams, and you're using the block and the 50-gram mass, then what's your new mass? 250 grams. So you don't need to keep measuring it. Measure the mass of the block with nothing in it, and then, after you're done that, just keep adding the masses to it and add them with your calculator or in your head. All right, that's the apparatus. Now, how are we going to use this apparatus? The first thing you're going to do is to determine the mass of the block and any masses in the block. So, in other words, like if you're using the wooden block and a couple of masses inside it, make sure you know what that mass is, what that total mass is. Whether it's by putting it on a triple beam balance scale or whether it's simply by adding the mass of the block, which you've already measured, to the mass of the aluminum masses inside it, whatever. Get the mass of whatever you're using for trial number 1. Then I want you to place the block and the masses that are in it, okay, whether that's 1 mass or 5 masses or 0 masses, place it on the ramp. But I want you to lift one end of the ramp slightly, but not enough to make that wooden block start moving. So in other words, we want to make sure that it's lifted a little bit, but not steep. Because if it's too steep, then that wooden block is going to start sliding, right? You can picture this right now, right? If you lift it too steeply, if you lift it too high, then the slope is going to be too steep, and then that's going to start sliding down. And we don't want that yet. Okay, we do eventually, but not yet. Now, you want to put the protractor down at the beginning of your slope. So let's go back to this page for a second. Can't see it real well here, but you can see that there is a protractor there, and you can see that the little crosshairs of the protractor, this is the middle of the protractor, go at the very beginning of your slope. This is the angle that you would want to measure right there. So whatever your protractor reads right there is theta. Does that make sense? Put the protractor down so that it can measure the angle between the floor and the incline. Then I want you to slowly lift the ramp that you've already lifted a bit. Slowly lift it a little bit higher slowly, 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 until the block begins to slide. When that block begins to slide, the F parallel, the force pulling it down the hill, will be equal to the maximum force of static friction. That's your way of determining what FSF max is. Does that make sense? Get F parallel. That gives you FSF max. But to get F parallel, you need to measure that angle at which that occurs. So back to this. Okay, let's say that I lifted this end up so that this block started sliding. That's when I would measure this angle, measure and record that angle. Now, it's going to take 2 or 3 people in order to do this. Okay, you're not going to be able to stand at one end and lift this up and hold the protractor and measure a perfect angle and so on and so on and so on. It's going to take at least 2 people to do this effectively, maybe even 3 people to do it effectively. Measure that angle at which it begins to move. And then you're going to repeat the first 5 steps, but each time with a different mass. So from trial to trial, you're going to do step number 1 through 5 with one mass, see what angle the block begins to slide at. Then you're going to do it with a different mass, and now see which angle it begins to slide at. And now you're going to do it with a different mass and see which angle it begins to slide at, and so on and so on and so on, at least 10 times, so that you have at least 10 different values of mass, and you have at least 10 different values of theta that correspond to those different masses. Does that make sense? Now, you're not going to plot a graph with mass and theta, although it seems like whenever we see a data table, we plot a graph. In the end, we will, but we're going to change that table into something else first. So it starts as mass and theta. This is our data that we collect in the lab today. We're going to change that into normal force and max force of static friction. Now, how are we going to do that? This is a spot where maybe you want to take a little note here. If this is our block, and this is theta, this would be the force of gravity. This would be the normal force, and this would be F parallel. Remember, the point at which this block begins to move, then F parallel will be equal to the maximum force of static friction. So we need to get FSF max here. Well, the way to get that is to get F parallel. So how do you get F parallel? You're going to say, just like we have in class a number of times, we're going to say sine theta is equal to opposite F parallel over m times g, or F parallel is equal to mg sine theta. You're going to calculate F parallel 10 times. That's going to give you 10 different max force of static friction. So remember that. You get F parallel, then you've got the max force of static friction. Now, what about the normal force? F parallel is mg sine theta. How are you going to find the normal force? What side of the triangle is that normal force? It's adjacent. So we're going to say cosine theta is equal to the normal force over gravity, which means normal force is equal to mg cosine theta. So get the value of the normal force for each trial using mg cosine theta. Get the value of F parallel, and therefore the maximum force of static friction 10 times for each trial, and then using mg sine theta, and write it into your table. And then, once you've done that, I want you to plot a graph of max force of static friction. I just see here a little typo that I've left off the x-axis here. This should be, what do you think should be on the x-axis? What should be down here on the x-axis? Static friction force on the y-axis, normal force on the x-axis. And that's going to be measured in newtons. The title should be y-axis versus x-axis, or max force of static friction versus normal force. It should give us a straight line. Now, I'm going to show you a technique that we use a lot in Physics 30, and we use the odd time in Physics 20, but not as much. This is something that we have to be really familiar with in Physics 30, so it's kind of your first glimpse of this. What equation describes this or any other straight line graph? Y equals mx plus b. Y equals mx plus b. Now, on this graph, our y-axis is FSF max. Agree with that? This equation, y equals mx plus b, tailored to this specific graph, would look like this. FSF max is equal to m. What does m stand for? Not mass, no. Somebody said it? The slope. I'm going to write the word slope in there. Why do I want to write the word slope in there as opposed to keep it as m? Yeah, I'm going to get mixed up with mass, right? If I leave it as an m, we're going to get it mixed up with mass. So we're going to write the word slope in there to avoid that confusion. The x-axis is Fn, the normal force. What does b stand for? Y-intercept, and in this case, it will either be 0 or close enough to 0 that you don't need to worry about it. Now, on your data sheet, you see an equation that says this. FSF max is equal to mu times the normal force. So I got an equation in blue here that comes from my graph. I have an equation in green that comes from my data sheet. Now what I want to do is compare those two. I'm going to cross off FSF max, because it appears in both. The equation from the graph and the equation from my data sheet. I want to cross off Fn because it appears in both. The equation from my graph and from my data sheet. What am I left with? Well, in this one I'm left with the slope, and in this one I'm left with mu. So what we're saying here is that the slope of this graph is equal to the coefficient of friction. You guys remember what the problem was? What was the problem? What's the coefficient of friction? So if you get the slope of this graph, you've got the coefficient of friction. Does that make sense? Well, then you have to draw a conclusion. The coefficient of static friction between these two dry wooden surfaces is, it's probably going to be in the range of what? 0 point something, yeah. What exactly is it going to be? Don't know exactly, but it's probably going to be 0 point something. If you get 7.3, well, I was going to say you're probably wrong. If you get 7.3, you are wrong. Okay? So try again. Could mean that you've just done some kind of unit conversion wrong or something like that. This is known because, well, I'll just briefly describe how you determined what that coefficient of friction was. Basically, you could say, well, it's the slope of max force of static friction versus normal force graph. And then, of course, your sources of error. We want 2 or 3 really good sources of error, things that could have been better about this lab, and then suggestions for improvement. So if you list, don't use this one, okay, because it's a pretty simplistic one, but it works. You're not going to use it because I'm giving it to you. Let's say you used that this ramp might have been dirty and therefore have an inconsistent coefficient of friction. Make sense? What would be the solution to that? Clean the ramp off. Okay. So now that I'm telling you that, what should you probably do before you do this experiment? Just wipe the ramp off with your hand or with a piece of cloth or paper towel or something like that. Yep?
How many do you want, 2 or 3?
Well, my general rule of thumb is this. If you have 2 really, really good sources of error and then suggestions for improvement, I can live with that. If you have 3 decent sources of error and suggestions for improvement, I can live with that. If you don't have 2 very good ones or 3 decent ones, then you should try again. Because 4 mediocre ones don't work for me. 2 really good ones or 3 pretty good ones, or try again. Make sense? So what do you got to hand in for this? You have to hand in for this a problem which I've already given you. You don't need to restate it. Just write down the problem that I've given you. Put a little star by that because you don't have to come up with that on your own. You do have to come up with the variables on your own. Manipulated responding control variables, although I kind of gave that to you as we were going through the procedure. The materials, which I also gave to you, explicitly gave those to you. What else do we need? You don't need a procedure. You do need data, which is that first table. Remember that first table of mass and theta? You need analysis, which is that second table that is normal force and static friction, and then your graph and everything on this page basically is analysis. And then finally we need conclusion, which is what is the coefficient of friction and how do you know? And then you need your sources of error. 2 or 3 good sources of error. Some people call that sources of error evaluation, whatever you want to call it, I don't really care.